So we're going to start talking about when waves encounter a boundary, and there's a number of things that can happen. The one we're going to talk about first is called diffraction, but there's also going to be reflection and refraction, dispersion and diffusion. So there's going to be a lot of vocabulary, and the words sound kind of alike, so you're going to have to be paying attention and maybe studying your notes as we go through this. So diffraction is defined as when a wave bends behind a barrier. Okay, now I'm going to give you an example. I'm going to use this folder as a barrier and I'll put it up in front of my face. You can still hear my voice, but you can't see my face. The reason why, the sound waves can bend around behind that barrier, but the light waves can't. We have to talk about why. So one thing we're going to say is that long wavelengths bend more than short wavelengths. And in the last couple labs we did a sound lab, and we found that the wavelengths of the sound were roughly about a meter. So on the same order as the size of this. So they could bend around it. Light waves are on the order of 10 to the minus 7th meters. We found that for the laser, which is a millionth of a meter. So way, way smaller than this barrier. So that small wavelength can't bend very well. And I have a little thing that shows that. Okay, I'm going to get this thing running, and we have these waves coming toward the barrier. I'm going to pause it for a second. Now, these represent the crest of the waves, so the crest-to-crest distance is the wavelength, so the wavelength would be about this far. And the gap in the barrier is much wider than that. And there's a little bit of diffraction, but not a lot. Okay, you can see a little bit of it bending behind, but if I was over here and this was a sound wave, I wouldn't be able to hear it, okay, because it's not bending that much. But if the barrier, the hole in the barrier, gets smaller, right now it's about the size of the wavelength. Wavelength is this far, the hole in the barrier is about that far. It's starting to bend noticeably behind the barrier. So if I was over here, I would be able to hear it. Okay, so there the waves go. They're coming like this, but then they're bending out behind the barrier. Now, if I continue to decrease the size and make it much smaller, now you can see it bending around behind. And I want you to notice the shape of these as well. Okay, they're almost circular, and they look like ripples. And when we had a single source, we would say that the waves go out in circles around that source. So this gap is acting like a single source of these waves. Going back to our notes. Okay, we want to say that diffraction becomes important when the wavelength is about the same size as the barrier. So again, the sound waves are roughly the same size as this, so they can bend around. Light waves are way, way smaller. However, if I had a really small barrier like a hair, then the light waves might be able to bend around it. Or if I had a very, very, very narrow slit, light waves can diffract through that. And we're going to see that in a lab that we're going to do. Next is two-slit diffraction. So now I have two holes, okay, and behind each hole, the waves are going to diffract around behind it in these circular patterns I was talking about. If the holes are very small, you end up with these circular waves going around just like these were sources of individual waves. And then when you get that together, they're going to interfere with each other, just like we saw with two-point sources. And we would use the same equation to find the angle between, say, the central maximum and the first order maximum.